For part A, we're going to recognize that at the very instant that the battery starts to charge the capacitor will hold no voltage. So this is at T equals 0 for the most part. So all the voltage that's being felt is from the battery, not the capacitor. So if I want to know the current that's coming into the capacitor plates, all I have to do is take Ohm's law, V equals I R, where V is only the voltage from the battery. Now, had the capacitor been charged a little bit opposite of the battery, you would take 70 minus the voltage from the capacitor. But since it's 0, we just say 70, and R is the 2 ohms, that is the resistance in the wire. So I is V over R, which is 70 volts divided by 2 ohms. And that comes out to be 35 amps. Now for part B, I have to do a little bit of sleuthing. I see that I have the capacitance, the area, the voltage, and the resistance that impedes the charging of the capacitor. And for part A, I need to find current, so I'm done with that. For part B, I need to find the change in the E field between the capacitor plates. So I need to find the E field between the plates. Well, I'm going to go ahead and use one of Maxwell's equations that seems to use the most of these things. First thing I recognize is that with C and A, I can find, or sorry, with C and V, I can find Q, the charge on a particular capacitor plate. So I can go ahead and derive Q somehow, but that at least gives me something to work with. So I have Q, I have all these things, and I need E. So the best thing to use is Gauss's law, where we take some sort of closed integral of E going through some area dA, and having that equal to the total charge enclosed divided by some permittivity constant. And in this case, Q enclosed will be that of the capacitor. So let's go ahead and look at the bottom plate in a bit closer fashion here. So my Gaussian curve is going to be like this. The reason why I made it square and not circular was because I wanted E to be totally parallel with the area vector on all parts of this side here, okay, of this side of the Gaussian enclosement. That means that the E field, assuming that the problem, I think the problem said that there is no E field outside the edges of the plate, that means that all of the other areas here won't have an E field. So that's all 0. The only E field is at this particular side, and not even on this part of the side, just the side that has the length of the capacitor plate itself. So what I'm going to do is I'm going to go ahead and say E then is 100% parallel with that particular area, A. So that's going to be E, A. That simplified the integral quite a bit. That's going to equal to the Q of the capacitor over epsilon naught. And this is Q on one plate. And when we say Q of a capacitor, we mean Q only on one plate because we assume that the other plate has the same but opposite charge, negative Q. So here's our equation. Actually, let me go ahead and go one step further. Now, to find the change in electric field, we'll take dE over dt. And the only thing that varies is Q because it's continuously charging over time. So we will have a constant 1 over epsilon naught A and dq dt over dt multiplied by it. dq over dt is just the current I. So that would be I on top divided by the constant epsilon naught times A. Now let's look at, all the pieces we have. We can just plug and chug from there. So A is going to be the 0.01 meters squared. So they gave us 100 centimeters squared, and that's just going to be 0.01 meters squared. I is what we found in part A, 35 amps. And then epsilon naught, it's kind of a big number. It's going to be 8.85 times 10 to the negative 12. But the units are going to be seconds to the fourth amps squared divided by meters cubed kilograms. Okay. So solving this out on the calculator, 35 divided by this big number and all of that divided by 0.01 comes out to be 4.0 times 10 to the 14th power. And this is where it gets crazy. You're going to have amps on top. Then you're going to have on the denominator this fraction. So you're going to put the denominator of the denominator on top as well. It's going to be meters cubed kilograms. And now the denominator will consist of seconds to the fourth amps squared meter squared. We're going to go ahead and cancel a few things out. This turns out to be meters kilograms per seconds fourth amps. And if you look up the definition of a volt happens to be meter squared kilograms over seconds to the fourth times amps. So this all ends up being eventually 4.0 times 10 to the 14th power volts. But since it's M instead of M squared, it must have been volts per meter. And that is the answer for letter B, the change in electric field between the capacitor plates versus time. Now for part C, if you don't mind, I'm going to turn this paper over a little bit so I can get a nice vertical space for the calculations here. Now what I'm seeing here is I need to find the B field that goes around the plate. So I guess if they're circular plates, for example, they go around the edge of the plates due to the change in the E field. And the only Maxwell equation I could see that has the B field term and a change in electric field is the Ampere-Maxwell's equation, or you could just say Ampere's equation. And that comes out to be a closed loop B field going in the direction ds is equal to mu naught I going through that Amperian loop. So that's kind of the equation we used for a very long time in our previous problems throughout this term. But now we have that added mess of epsilon naught mu naught d flux electric over d time. Okay, so let's go back to the drawing real quickly, and I'll put the drawing sideways here. We're going to look at the B field going in a circle around the gap of the plates. Now, going through this actual Amperian loop is no current because the current stops at the plates, right? So the only thing that goes through is the changing electric flux. So the first term ends up being 0, leaving only the second term. So now we have this changing B field, this B field going in a circle equaling to epsilon naught mu naught d phi e dt. Okay. But now we also have to understand that what is the electric flux? The electric flux is the electric field going through an area. So you can now say that phi e is really just E times the A, which is the area of the circle, which happens to be the same as the area of the capacitor plates. So now we're going to skip that or go to the next step. Again, you got the left side of the equation equaling to epsilon naught mu naught A dE dt. Now, since A doesn't change, it comes out of the derivative. Now we're going to just look at the obvious. If it's circular plates, at least, oh yeah, it does have circular plates based on the problem. Then the B field is going to go in the circle. So we can say that the Amperian loop is that of a circle of 2 pi r, r being the radius of the plate. So we can go ahead and say B 2 pi R, which we haven't defined yet, but we'll get back to that later. Well, we have defined it, but it's not within our allotted variables that we are allowed to use here, is going to be equal to epsilon naught mu naught A, and we have dE dt, which we already know from part B. Next, let's go ahead and isolate B. B is then equal to epsilon naught mu naught. Now, instead of A, let's do something interesting. So instead of A, we can turn it into R, or we can turn R into A. The equation that we should probably use is area is equal to pi r squared. So I think it would be better to turn it into A since we know A, but we don't particularly know R. So we can go ahead and keep A here, dE over dt here, and then you're going to divide it by 2 pi, but instead of R, we're going to go ahead and call that A over pi rooted. And if you want to simplify this, it's going to then be epsilon naught mu naught. The pi here will go up on top and it will cancel out with the root of this pi here. So it'll be root pi on the bottom. And then this root A is going to cancel out partially with the A on top, making it a root A on top. So we're going to have we're just going to actually put that all in one term, or part of a term here. We'll have 2 here, and then we're just going to say multiplied by the square root of A over pi. We have all the things we need to know. We know epsilon naught and mu naught from the internet. We know dE dt from part B. We know A from what we know here, so what was given to us in the beginning, and 2 and pi are both just constants. So plugging that into your calculator, we get 1.2 times 10 to the negative 4. Okay, now this is another way of analyzing units. So the first time I did it for part B, you'll see that I had a hard time trying to get all the units into a nice form in the end game here. Now, you can spend your time analyzing units, but here's a good little kind of a cheat. If you use SI units for all parts and you know that the physics equation is correct, you use SI units for everything in here. So this is in meters, this is in whatever, this is in, you make sure that these are the SI form. You know that this is in, what is it? The electric field times the area over time, whatever the units come out to be here. If you make sure they're all SI, then you can bet that the end answer will be in SI units as well for B. So in this case, if I make sure that everything was in SI units as I plugged in the correct value of the numbers here, I will just have to assume that the ending unit will be Teslas, because that is the unit for magnetic field. So let me go ahead and show you what I did here. This is part A, finding the current at t equals 0 that charges the capacitor. For part B, which is finding the change in the E field over time in between the capacitor plates. And then part C, finding the B field due to the change in E field between the capacitor plates.